Well, good morning, everyone. So it's my turn to finish the series of talks. First off, I have a few mistakes to correct, which I corrected in the notes, but to be sure, there was an obvious condition in model VLC which I missed. It was so obvious, so now it's changed. And yesterday I was a bit tired at the end, so I mixed up the two definitions. Nothing special. So there is one last theoretical object I need to set up before I actually finally can explain to you what quadratic Chabauty really does in this context. So this is the notion of curvature. Curvature form, to be precise. But first I felt I needed to explain a bit more about what the Chern class does. So if you remember, I have this, which is quite abstract here. I have a map from Picard group to second de Rham cohomology group. And what I should say is always what's implicit here is that for X over C, you also have a map from, or here I should say, I also have a Chern map that goes into slightly different space here, which is this. And how is it defined? Well, basically, this is quite classical, but I will explain. You have this exact sequence of sheaves where this is exponential to I pi times this, which is why it's 0 in the integers. And because of this exact sequence, you end up with H1 XOX star, which is this, sends to H2 XZ, which is there. And actually, the two maps can be compared. And well, I just say, because I want to be vague, they're all basically the same. Okay. All right. From this, and you don't have to remember much more about this, except that first off, the kernel of the Chern map is actually something you know, which is peak 0 of X here. I actually could not find a proof of this in this context over general K. I know how to do it without by going through C, but maybe if someone knows what's a formal proof, I'd be happy to hear about it. And the second one for X abelian variety. Okay, inside C again. Here. I'll just say this, but it's actually how we should think about it in many cases. This lives in H2 de Rham, so it's a bit complicated, but over C, it becomes more manageable cohomology space. And there you have the Hodge decomposition in this case, which means you can split into two forms, 2, 0, 1, 1, and 0, 2 forms, all right? And here it makes sense that T1 of L is always secretly, I should say it like this, secretly a 1, 1 form. Okay. And when you go to C, you will get this. And for abelian varieties, actually, you can describe everything quite explicitly, and you can figure out precisely what this form is. That's basically all I need for what happens next. So let's go. Okay. I take X over K proper, still smooth. I take L bar is equal to L endowed with the log function. If you remember a log function, so in the fibers, satisfying nice properties. And maybe I should remember one which was maybe not obvious. But, sorry. D log L was defined by sort of primitiving derivative of something that's obtained by one-time integration of Kalman function. All right, so there is a cup product here from omega 1 x for h1 de Ram x to h2 de Ram x. I drop the over k everywhere here. Simplify and assume C1 of L, the Chern class of L, is inside the image of this. It's not very difficult, actually, it's automatic. For X curve or abelian variety. For curve, this is quite simple. This is one-dimensional. For abelian varieties, you can, again, describe everything over C at least, and you realize that this doesn't raise any issues. So C1 of L is in the image of the cup product. And then there exists a unique alpha, which I define L bar here, such that, so I should mention where it lives. So in this place. Such that, and now there is a strange formula, which I will try to explain a bit afterwards. So pi star alpha L bar, so I should remember pi goes from L to X is the canonical projection, making this a line bundle. So this should live inside the same object, but for L star here. And I can compare it with delta bar D log L. Recall you as well, delta bar is defined always something like over X or over L, it also exists. And it goes to H to the round. So there is one here. Okay, so I should have this equality. And maybe I should right now see the link with the Chern class. Because of this, I can also figure that the cup product of this one, so it's an element of this, so I can apply the cup product. I get something in H to the Ram, and it's supposed to be exactly the Chern class. Okay, so I cannot say much more about this, but what you can maybe think about here, that C1 of L acts as a sort of topological invariant. Right? It only depends on the line bundle, so it's some sort of rule you have to satisfy. Okay, so this is really attached to it, and now you want to find a good way of having this and a good choice for this. All right, and I suppose conversely, if you have a product of some alpha is equal to C1 of L, you can find a function log L with this function, this equality holding. Okay. So to be honest, I don't find it at first very intuitive, but I'll try to explain at least why this might be interesting. And to do this, just first remark, I have not done it yet, but I can compare two logarithm functions on the same line bundle. Okay. If I take log L prime, okay, on L, so two different functions here. The difference, well, has to be constant on the fibers. Okay, because I just look at how I am supposed to act on each fiber, and on each fiber up to translation, it's exactly the logarithm map on QP star, right? So the difference has to be constant. So you can think of it as being something that lives in X, function of X QP. Here, what's more, and d log L minus log L prime, if alpha L bar is equal to alpha L prime bar. Now you think about what if this condition is satisfied for the same alpha here, where you differentiate here, this is equal to 0, okay? But if you remember how we define delta bar, we know the kernel of this map. Kernel of this map is exactly, oh yeah, here, sorry, this was the end space. It goes from omega 1 v1 of x to omega 1 of x tensor h1. Right. Now this is good. So, and this map has kernel exactly omega 1 of x, the old regular forms we have before. So this would mean that d log L minus log L prime belongs to, so it's a one form on L star, but also invariant. It should be in pi star omega 1 of x. All right. So in other words, we have log L minus log L prime should be some primitive of omega or omega inside omega 1 pi star. All right, so now it's immediately quite interesting why we do that, because if we fix this choice, the indetermination of log L is up to something we already know. It's a one integral of a one form, on a regular one form. So now the idea is there now with this degree of liberty, is there one good choice? Answer is yes, and I'll prove it. Not really, I'll just say it. So the theorem is the following. So I take L symmetric on A. I take alpha in omega 1 of A. So again, a Boolean variety. Here, I take alpha in omega 1 of A and sort H1 Berram. Such that the cut product applied gives me the Chern class. There is a unique good. Oh yeah, I should rigidify. It doesn't matter if at the end doesn't change, but I should rigidify it anyway. A good log function here, such that L bar is equal to alpha. Again, L bar is equal to L log L. Okay, there is a unique choice of log function having the right curvature form here. And it is also symmetric here and normalized. I haven't given it a name before, but this is log L of R is equal to 0. Okay. To recall, once you have rigidified your line bundle, you know this happens for symmetric line bundles, okay? But now you have rigidified, you can rigidify this, this, and all this. So there is a unique isomorphism of rigidified line bundles going there. And that's when you ask, is it an isometric, right? And now, in this case, you have a unique choice here, and it happens to be also symmetric and normalized. I'll actually sketch the proof because it's quite interesting. There is not much to do once you have done everything like this. Okay, so start with the log function. Log L function with, oh yeah, sorry, I forgot to give it a name here. put it in red because it's important. This is called the curvature form. This curvature form alpha. All right. Well, when I do the thing, yes, I should also say it behaves well with fullbacks, okay, and with tensor products. You can. It's basically what you imagine in this case. It behaves well with regard to these things. So if you start with the log L function with curvature form alpha, well, you can look at log L tensor 4, okay, and this is isomorphic to log 2 star L. Okay, so you can compare them here up to isomorphism, which you have. You can compare those, all right? And because what I said here, they will have the same curvature form, which is 4 alpha here and here. So this is a multiple, actually, of some omega. Primitive of some omega here in omega 1 of A. So you have almost something that it should, you want it to be 0, right? You want it to be equal, but you have an isometry, but this is just twice omega. So you just do take log L minus pi star integral of omega. It will be good. So because of this, no, sorry, it will be good. So what I mean is that 2 star L isomorphic to L4 is an isometry. Okay, you can prove this just because of what you've just shown. And now you have this as an isometry, and you can prove that if you know this, you can extend it to this. Okay, so it's enough. It's just enough to look at what happens when you take followed by multiplication by 2. Enough for the good property. Okay, so actually, once you know what is the indetermination, it's quite nice. You just modify by an integral of something you know, one form, and you're good. All right. There is one last thing to make clear before I can explain a bit more. Actually, you have, again, maybe I should justify it this way. You maybe don't want to do for every line model a choice of curvature form. Okay, you could do this, and you know now you have a theorem telling you that there is a good log function, but maybe you don't want to do this for every line model L. So is there a way to do this for all symmetric line models L? The answer is yes, because if you remember from yesterday, we have something like this. We have every square of a line bundle symmetric is a pullback by something you know of the Poincare line bundle. So because the curvature form goes well with the pullbacks, if you choose a curvature form here, you obtain one here, and you can then decide to choose the good function there. So there is sort of one good choice to make here as well. Here you have that's omega 1 of A times A dual actually can split as pi 1 star omega 1 of A plus pi 2 star of omega 1 of A dual with the projections over A and A dual. And actually the same happens for HDR. Same. Okay. It means you have two pieces here, When in tensor, you have 4 pieces corresponding to the tensor products respectively. Okay. And you won't say that alpha inside the tensor product here. So is purely mixed if no term in, so for example, I1 star of omega A, 1 of A times and so A, and none either for the duals. Okay, you want only cross terms. And the second one is you want the curvature form, so this curvature form to be actually a hope of a form for a Poincare bundle, which means you should have this. All right. And actually, I will not explain here, but choosing such a purely mixed curvature form it's the same thing as choosing a supplementary space of omega 1 of A inside H1 Durham of A. And this is often a choice which is made when you look at p-adic heights. So it's actually equivalent type of choice. Also, you might suspect there is something going on here with this space. I didn't mention it either, but there is some sort of duality between A and A dual that also appears in the omega 1s and H1 Durhams. I don't really need to explain more, but it's also one reason here we want something that's purely mixed. All right. And now maybe you might wonder, okay, why don't we just make one choice of alpha like this without having too strong conditions here? Well, I guess it's for the next result. Quite beautiful. Next one. So for alpha, a purely mixed curvature form here as before. There exists, of course, a unique function log p here, which is also determined with these conditions. I mean, some good functions here. Okay, there is only good function log p, good logarithm function here, which is also determined by, and something quite simple actually. Well, this is something on the Poincare line bundle. Okay, so I restrict it to the Poincare line bundle, restrict it to 0 times A dual. Okay, so this lives now over A dual as a long function. The pullback of the Poincare line bundle over A dual. What is it? Actually, it's exactly the log A dual. So the logarithm function, which I defined in the first talk, over abelian varieties. And now restricted this to, so P star, yeah, to A times 0. Here, well, as you can guess, it's the same thing with over A. Forget log A. In other words, you have something. Oh yeah, and of course, here what's underlying here is that this is trivial as a line bundle. Okay, so you can really think about log A. So it's, if you evaluate this on a trivial line bundle, it's the same as looking, if you evaluate at the trivial at the one section. Okay, you get this. I should say A dual 1 is equal to A dual, and this A1 is equal to A, to be more precise. So you get back exactly what you have before for the A and A dual, and what it's telling you with some condition on the geometry, which is basically this. You can extend this to a logarithm map on the whole Poincare bundle, but of course you don't get anything really additive anymore. It's a bit more complicated than that. Okay, and now just to be clear, even though it's already understood here. Now, for any L, so L symmetric, alpha L will be half of this pullback. Call this alpha P. P and P. Okay, In other words, you have only this choice to make. Choose one purely mixed curvature form for the Poincare bundle, and then you can define good things for, you can define curvature forms for every symmetrical line bundle. And once you have defined this, there is a unique way to define a good love function. So now it's as canonical as it gets. Okay. So now I can finally put it all together into heights and explain why it works so well. While you're memorizing, do you have any questions? Oh, here you have this, the same thing with H1 Durham for A and A dual. Okay, so you have when you tensor product, you have 4 terms. You have the ones with only A, the ones with only A dual, and you want your projection of alpha to be 0 on those, and the rest is well, the rest has the right to exist, and then you want this to be, which is actually some sort of duality statement. Oh yeah, sorry, C1 of P. Yeah, thanks. It's the Chern class of P. Thanks. Okay, this here. Other questions? Good. Okay, I should share with you the good news now. We've done all the technical stuff we need to do. Now it's only a nice stroll from here. Just have to put it together and get the results. I'll show you some proofs. You'll see that now it's not too difficult. The ideas are all there. Okay. So, do adelic p-adic heights. First off, a small definition. I said to you that to make this function, we look at heights, local heights and line bundles, okay? And we want to deduce them heights, but on the points on the variety, okay? Not the line bundle itself. To do this, we take any sort of point above the line bundle, above X, and we extend, and we hope that it doesn't depend on this choice. To do this, we need the product formula, which was sort of automatic in other contexts, but here it's slightly more difficult. So we take a function like this, and here it will be simple. So if you want the pedantic version, this is a continuous Idel class character. Okay. And if you want the more practical version, it means you define chi v in MQ. So for every possible prime and maybe infinity here. So chi p will be minus log p on qp here. And for q different from p, chi q of lambda will be the p-adic logarithm of q times the order of lambda at q for all lambda in qq star. If you're wondering why I do this, it's to have something living in qp, and so that's the sum of all these values for lambda is 0. Okay, so just for product formula. Okay, of course here it's we write it in logarithmic form, so it's more of a sum formula. But this is more well known, so I still say products. All right, you can check it out. It's not very difficult. I don't define anything at infinity because it's 0. 0 is enough. We don't really care about what happened at the real place, so it doesn't change anything. Now, what is adelic metrized line bundled. The L, so let's call it for now symmetric. Sorry? It's times the order, yes. Yeah. For example, let's test it out. Let's take lambda is equal to q for some prime q. Of course, for lambda is equal to p, it's pretty easy to check. Yeah, is equal to p should be okay. Because because log of p is 0. Actually, log of p is equal to 0. So for lambda is equal to p, it's easy. For lambda is equal to q, I get log p of q minus p of q here and log p of q here. That's fine. And the rest is 0, of course. Yeah, and maybe that's a bit weird here, have minus value, because usually for heights over R, we like positive things. Here it doesn't really matter. We don't have a definite positive quadratic form, so the sign is really not a problem. So I took minus log p. All right. So I take L over x over q here. And I take what I denote L bar will be a choice of L, log L, and valuations. VLQ different from P. Okay. So log function, Q valuations, of course. And I had some compatibility condition almost all Q. Okay. Without entering too much details, that's also very standard. Even for the usual heights, compatible means you want to say there exists a model over almost all primes, and that this model defines the VLQs for those primes. Okay, and it's generally easy to build this kind of model because you might have problems with some fibers, but it's pretty easy to extend any sort of equations over X to something that will be well behaved over Z up to some denominator. But it's not very much of a problem. Okay, and here it will be called good if so here log L good and all VQs canonical, and canonical if this is canonical and other canonical here. Oh yeah, of course canonical here. So maybe I have to choose alpha. Alpha P here. Okay, I choose a curvature form for alpha for P, and then this will be called. Where did I write it? Okay. Canonical log function afterwards. Okay. Now, and that's what I will show, is that, and actually it's not a very difficult result now. The heights are defined with so much efforts are actually very nice. So if L bar is good, H L bar is quadratic. Okay, first thing. Second thing, if L bar is canonical for all A in A of Q, so here, of course, this makes sense only over, I can take here an element variety, be sure, even though it exists in other contexts. Here, for A in A of Q, well, H L bar of A is the same thing at 1/2 H P bar of A by L A by AL of A. So of course H P bar makes sense. You have a canonical height on A times H dual, again alpha P chosen here. And also chi chosen. We'll see afterwards. Oh yeah, so yeah, you don't define actually the height. That's why I left room. The height is what you imagine. The height of x is so minus log p of u plus the sum for q different from p of here v lq of u iq of u with u different from 0 above x and u inside L star of q. Okay, once you have all this, you have a sort of metric on every place. So you define this, the sum, and it's meant exactly because of this, so that if you multiply by a lambda here, it doesn't change the value here in total, which means if you take two different u's, rational, they differ by a rational number multiplicatively, so the height is the same. Okay, so that's why it's well defined here. Like this process. So now the good news is this is a good old function on A of q that's quadratic. And if I've done all the canonical choices, I can actually define it for this. And this, well, I know this is I know this is a quadratic already, but you can see here it comes from actually something that's a bilinear form. So here it's even better. It's a bilinear form, A of q times A hat of q to qp. All right, so there are three results inside this. I will not show everything. I'll just prove 100 points, but the rest is really proceeding along the same lines. Proof. Well, the first proof is quite easy. So if L bar is good, choose the reducification R. So in sort of q above 0. By construction, S star, if you remember, S is the sum from A times A to A, D is the difference, and P1, pi1, pi2, as written here, are the projections. So I use this, and I know it's an isometry for every place. By which I mean these are isomorphic, and because I have chosen rigidifications, there is a unique isomorphism from there to there, and I've done it exactly so that it's an isometry over every QV. Finite. We don't care about the infinite place. Okay. This was exactly the hypothesis for log functions, and actually for the evaluations, if you check, they are really even more canonical. You do the pullbacks, and this happens to be isometry. That's built in the statements. All right. So what it means that if I choose u above x here, so for any x, y inside A of q, sorry, it means I have H S star L bar of x, y plus H B star L bar, sorry, L bar here, of x, y is equal to 2H by 1 star L bar of x, y plus 2H by 2 star L bar of x, y. Okay, that's by equality here. But now the pullbacks works exactly as you imagine. So I just apply the map here and check what happens. This is H L bar of x plus y plus H L bar of difference x minus y. And now it's 2 times, I just forget about y here, h L bar of x plus 2, sorry, h L bar of y. And even term by term, if I choose u and v above x and y, I really do get term by term equality. The things are the same. And so I obtain this formula, which I guess you know from normally you've known for a while. This characterizes quadratic forms over any sort of Z modules. And you can even define, if you want to define the bilinear form, you take h12 bar of x plus y minus h12 bar of x minus h12 bar of y divided by 2. And you will get a bilinear form because of this. All right. So this explains why for a good, I get quadratic, which is already good news. This is a simple consequence of functoriality. I've done everything so that it works. So maybe the interesting part is, why is this bilinear? It's a bit stronger. I mean, I can say that as a form from a times a hat of q to qp, it's quadratic. It doesn't mean that it's really bilinear on both sides. So, and I just say one word about this. Bilinearity of HP bar. We use this fact at S star P. So here it's in A times H rule, right? It's the same thing as the product S star P, P1 star P times P2 star P. So S, to be precise, in here it's this. And the projections, okay? Well, this might be surprising because if you remember, I talked briefly about anti-symmetric line bundles, and they check exactly this isomorphism as well. All right, but P, I said it's symmetric. Well, yes, but it turns out, and the proof of this is like many others, you apply the seesaw principles, you look at what happens over slices. And it turns out, by definition of P, almost, over slices, it behaves basically like an anti-symmetric line bundle. So you can obtain the equality over slices, and then you deduce the equality over A times A dual. And because of this, if you translate what happens here, it tells you that here it should be, so, oh yeah, so maybe is the reason, check, x plus x prime y. Yeah, if you translate, it will tell you that h p bar is bilinear on the left. And then you can use some sort of symmetry to prove it's also bilinear on the right. Right. So now, finally, I can explain how quadratic Chabauty works out. We have, once I've chosen this, I have canonical choices and even have good choices if necessary, but they're less well determined. Okay. And I've finished this. Do you have any questions? All right, ready for quadratic Chabauty? Well, I should start what I erased by saying, ultimately, once I have good functions like this, it will rely on the fact I can produce even one good line bundle that will do what I want, which will define one, at least in the rank is equal dimension case. It will write one good function here, and I'll be able to use just this function to obtain the needed result. That's what I'll do now. The question is, what is a good line bundle? The ones I want to use. Oh, by the way, yeah, I should also say, and I should say it right now because it'll be useful afterwards. I said everything for heights attached to symmetric line bundles. Okay, well, that's not all in life. You also have anti-symmetric line bundles. Turns out you can define similarly all this, of course, taking into account that this is not more true. You have another formula, which I explained there. You have other natural properties of line bundles, but you can still define things which are well-defined and canonical. Okay, it's a bit simpler, but it's double the work at most. And also, I didn't want to do it. I should say, definition here like extends to, we have the remark. Can extend notions to anti-symmetric line models. And if you think about the fact that for an anti-symmetric line model, n star L is not L power n squared, but L power n, so it's linear, the conclusion is that you should have something linear. And you get linear good heights. Okay? And of course, and now you can add those. Because you can, if you take any line model, you can take L times 1 minus star L, which will be symmetric, and L times 1 minus star L minus 1, which will be anti-symmetric, and you get the square of the original line model by taking the product. So up to just dividing by 2, which is fine. You can define heights for anything. The symmetric part will be quadratic in the height, and the anti-symmetric part will give something linear. All right? Just to convince you that you're allowed to do this. So now I start by discussing what are the good line models we want for quadratic Chabauty. Okay, maybe let's start with the hypothesis, and I will only explain things for R is equal to G here, and with rho larger than 1. If you remember rho, what is it? Rho is the rank of the Jacobian. Sorry, of the Jacobian here. All right, and this is our group carried by x0. All right, so I won't say that there is something non-trivial in there. Well, I have iota from my curve C to J. Again, so Abel-Jacobi map sending a point P to the class of, oh, it's been written here before, P minus B. All right, and by pulled back, everything goes well, and I can define iota star from J to pick X, and from it also restricts to the peak 0 here, which means I can define a quotient iota star ns from ns of j to ns of x. Okay, but for a curve, oh, sorry, I should say C, I want to say it's a curve. For a curve C, this is isomorphic to Z via the degree, at least here because I have a rational point. So this is really the degree. So I have something that's a Z module of rank rho going into something of rank 1. So saying rho is at least 1, at least 2 actually, means that there is a kernel in there. Okay, kernel means there is a L, not in peak 0, that sends to something of degree 0 on C. But actually, that's first step. That's not enough. That's not exactly what we want. What we want is something that becomes trivial. When I pull back, and I explain it right now. Small lemma. The kernel of this map here is isomorphic to this group of L inside peak of J that iota star is trivial. Okay, so it means OC, the trivial bundle on C, and I quotient out by the ones belonging to peak 0 of J with the same property. What's pretty obvious is the inclusion. Okay, if I take this, in particular, it has degree 0 as a divisor. So I land inside the kernel here. And of course, I go from there to here. The kernel is given by things belonging to peak 0. So this is immediate. Now the question is how to go from an element in the kernel to something like this. So, and this is where it's quite interesting. Take a class L0, let's say, in a kernel. Okay. The only thing it means is that iota star L0 is of degree 0. All right, that's all. I just land here and I want degree 0. That's the kernel. I want to modify it so that it's not only of degree 0, but actually 0. How do I do that? Well, now I can remember, and that's one of the properties of the pick 0. I know what pick 0 of C is. Now, I use the second map here. Pick 0 of C is actually the same thing as J of Q. By definition of the Jacobian, one of the definitions at least. So what I have here is actually an element of the Jacobian. All right. Now let's take an M line bundle in pick 0 of J. Okay, another one. I will modify L0 by M because I don't want to change the class. I want to stay inside here. So I want to take an M. I will modify L0 by M. I hope I modify enough. But now what happens? If I take M here, I go to I star of M. Okay, so this defines something in the same class, which is fine. So it's also an element of J of Q, but I might not be sure of what happens here. And now remember, pick 0 is also here. So J of Q here. Pick 0 is also the dual of J Q, by definition of the dual abelian variety. And this, which is iota star, is actually given also by a commutative diagram here. And there is a map from J dual to J. And one property of the Jacobian that's quite special to it and not true for all abelian varieties, that there are maps like this, and this map actually is an isomorphism. Here. If you remember, to give you some words, it's because it's principally polarized by the theta divisor. So first, this gives you such a morphism, and then you can prove it commutes, or maybe anti-commutes depending on the convention. But I didn't specify the isomorphism, so it's fine. Here you have an isomorphism here, so it means this map there is also an isomorphism. So find iota star M such that iota star M is equal to minus iota star L0 in J of Q. You can find that. So then you can pick L equal to L0 tensor M minus 1. It will have trivial pullback. Okay, so now we know for row at least one that this is non-trivial. It means this is non-trivial. Okay. So we're sure we can find a good L, and that's exactly what good L means here. It means we can find such an L, so we can find, we fix L inside pick of J. I'm not in pick 0, such that iota star L is the trivial bundle on C. And now it means, and this is where it gets very good, there is a canonical map from C to L, which lifts the map here. So I'll draw it. This is iota. L lives here, all right? If you remember, the pullback is something living above C. There is a map naturally defined here. Okay, but now what I know now is that this is isomorphic to OC. So in other words, as a line model, I can say it's isomorphic to C times A1 here. So I can define by the section 1. Okay, I can lift the section 1 to every C. I said C1 here. I go through this and I go there. Finally, it defines me map from C to L that lifts the map from C to J. And actually, you can check it's an equivalent condition. That's this condition, the existence of such a lift gives a condition. And so now, well, it's pretty easy to do. I can check, I have a height on this, actually L star, I should say. It goes to L star even, because I go through the section 1, which is number 0, so to L star. So there's a map from C to L star, which define easily a height. I define HC of X will be H L bar of, so H L bar of here, wait, phi of X. Okay, so I have a height defined over Q points on C. And now the game is just to show that it has the nice properties that allow me to isolate rational points inside QP points. All right. Of course, I take a here. Let's take canonical height, but I could take another one. Here. All right. First remark. If C has good reduction at Q, the quadratic contribution to HC of X is always 0. So quadratic means the one coming from the what happens over Q. The reason, because in this case, I can define an integral model variation over J actually, and I can pull it back over C. And here I'm looking at, it means I'm looking at what happens in the one section. And the one section will be also the one section for the integral model. And because of how I've chosen the integral model variations, it will be 0 all the time. Because I'm really landing inside I'm sort of at the right height in the fiber, because it's always 1. So this will not contribute most of the time. First, which means as a corollary, because it's true for almost all Qs, and also I can say the VQ, it's one of the hypotheses, if you remember, it's locally constant. The VQs, so it means even if this doesn't happen, at least I know that the periodic contribution lands into finitely many possibilities. Right, so there's some also, which is something you've already seen in the previous talks, including Jennifer and I think Nathan as well. So here, what can we say? We can now run Quadratic Chabauty. So assume, so the rank of log of J naught of P of J of Q, sorry, here is equal to J D in the tangent space here. Recall, even if I assume the rank is equal to G, I mean, as a rank of J of Q, it might reduce when I apply the log, okay? But if it reduces, I have a vanishing differential as a classical Chabauty. Okay, so if it reduces, I'm fine. So it's really okay to assume this when I want to apply quadratic Chabauty. It means over there I do have a quadratic form, because this is the same actually. Same as J of Q tensor QP here. So I have something on J of Q, which is defined by this. So I have H L bar quadratic on J of Q, actually even tensor QP actually. This extends. So this defines, because of this, a quadratic form on this kind of space is given by a basis of products of linear forms. I choose the basis of linear forms. Basis of omega1 of j. They can be rational here. It's not a problem. But here I will need QP coefficients. I can write HL bar of D is equal to something like this. And what are the linear forms on this? As I said, if you remember, linear forms on a tangent space can be given by exactly p-adic integration. I can write all this like this. Okay, well, this was if it was exactly quadratic, but there might be a linear term. And if you think why, actually, I think we can manage taking an L that's symmetric until here. But here we need to modify by something in peak 0. And there we might need anti-symmetric land models. Okay, which is why I just said this remark before. So this was the quadratic part, and the linear part is even easier. Some I of Ci omega I here. So we have this on J of Q tensor QP. Okay, in particular, so for all P inside C of Q, I can write HC of P will be of Ij, A Ij, this integral here, and I should say here it's all the pullbacks on C, right? Because they live on J, but the pullbacks live on C, and there is a bijection. So I'm a bit lazy with the identifications, but that's the idea. So I've written something that's a height that has a sum of things here, and this, well, oh yeah, so yeah, I forgot some, I forgot other terms, so I'll write them. No, so this is good. Okay, this is one of the ways to define it. The other way is to remember what is the definition of the height. And this is where I get the second equality. Because remark, this extends to p-adic, to C of QP, right? You can extend this as a definition, it's a p-adic integration. It makes sense over QP. And I'll make the same thing. Maybe I should write it. Sorry, I'll have to go back to the other way, but you'll have two very different writings of the height that are at extreme sides of the board. So once you have this, you can also write here H L bar of iota of P here. So it's not exactly iota, it's phi of P here. It's the same thing as minus log L of section, I call lazily P1 here, plus sum from Q different from P of KQ of, yeah, here I should write here's KQ applied to, sorry, let me check. KQ, DQ P1 here. Okay, apply to the section. This, as I said, is some value T belonging to T, a finite set. Okay, every rational number, there is no problem with this. It's really finite. It's not very easy to compute, as Jennifer explained sometimes, but for us, we're happy it's finite. And this, well, it also extends to C of QP, right? It's just defined over the whole p-adic points if we want. So we have two functions now that have quite different aspects. This kind of p-adic logarithm function plus something finite equal to a combination of products of integrals. This is exactly, to tie up with what I said in the first talk, this is exactly what defines p-adic local equations of rational points. So I can define ft. Also, how did I normalize it? Okay. I can define ft, which is the sum of those integrals over there. I plus log L of 1. This is on C of QP, well defined. Okay, so now we have to solve for this is equal to T. So C of Q is included in the union, or T is inside T, Ft minus 1 of T. Yeah, actually, here there are no unique functions, so I should say minus T. Minus 0. All right, is it minus plus T? Okay, so I've isolated rational points inside these 0 sets. There is one last thing to check before I can be happy and say I have a finiteness. What is there to check now? What would completely make the method fail here? Yeah, it might happen that I have 0 locally or a constant. If f is a constant, well, a constant equals to 0, I cannot say much, right? So, thing to check. Ft is not locally constant anywhere. Okay? Because otherwise, of course, this can happen. It might be infinite, even the whole thing. But now the hope is that I've built things enough that I'm sure it's not locally constant. Why? First, given how it's built, it's iterated integrals. So it's what I called yesterday Vologodsky functions. And there is an isolated zeros principle there. Okay? So because of this, it's enough to check that Ft is not constant. It's enough to check that here the differential Ft is non-zero. Okay, I'll just say this. And everywhere here means non-zero as a function here. Well, I'll now analyze what's going on with this function and prove finally that there is no problem here. So this means I want to prove this is non-zero inside omega 1 C over QP, or at least the Vologodsky 1 forms. So let's check. So df, what is it? Well, I just compute what it should look like here. Ij, sum of ij, aij, and there I differentiate either side, so it gives me this integral times omega j plus the other integral, so omega I. There it gives me the omega I, and the log is just for now a d log. Well, still for now it's not clear. It's non-zero, right? Well, we'll just apply one more operator, which is delta bar. Here, that's what gives us our information. Delta bar df now is the sum ij. If you remember how it was defined here, delta bar, this is actually ai. So because long ago I had the definition of delta bar, and what it does here is gives you omega j. Is it tensor omega I? That tensor omega j. Remember correctly? It should be this plus sum of ai here. So this is 0. This disappears because delta bar vanishes on regular 1 forms. So I get this, and I get delta bar d log L applied to P1. And now I want to say that this kind of thing does not belong to the same space as this kind of thing. Okay, so I'm looking at things now inside omega 1 of C tensor H1 of C. I'm comparing, and I won't say this object is not the same thing as this object. Okay, in degrees 0 and 1, looking at C and looking at J is the same thing. So I can compare them over J. So right, sorry, is it yeah, here, and over J, what happens? Over J, this actually is alpha L, okay? And apply the cup product. Okay, what I'm pretending is this. This secretly, again, if I think of things over C, I take cup product means wedge product, and I have one form that's holomorphic times something that's one form, any sort of one form. This would be in omega 20 plus omega. Actually, yes, sorry, actually it's omega 20 here, because I look at one form that's both holomorphic. So in this space, this belongs to omega 20, secretly over C, but this one belongs to omega 1, as I said. Okay, if you look at over C, it has type 1 from 1. So it means they cannot be equal unless this is 0. Okay, so delta bar df different from 0 unless. So the cup product of alpha L is 0. Okay, but what is this? It's exactly C1 of L. And I've asked specifically before that C1 of L is non-zero because L does not belong to the Picard group 0. Okay, so I'm sure this and this do not belong in the same spaces for the decomposition that's implicit, which forces this to be non-zero. So DFT is non-zero everywhere. So this means that I do have actual equations here that isolate my rational points. Okay, so this was the Chabauty method. So once you have set up everything, it's enough to have one of these functions, and you'll prove afterwards that it lags. And well, Jennifer said a lot more about this than me. But now you have to compute this. This might be a bit difficult, but then this is a logarithm. Hopefully you can identify it in some other ways. And this has to be determined by solving for a. You have to calculate values for a basis of J of Q and then determine the equality here, basically. To solve for all this. Okay, now I can explain some variants and what we can hope to do afterwards once we have this. The first one is, because that's one of my favorite subjects, I won't say what happens on the quotient. If you find a good quotient of J, what can you do? So I have this now. All right. First, assume we have J goes to a quotient with rank is equal dimension. And row A, so non-severity rank here, is also larger than 1. So same thing as for a J of Q, but for a quotient, not the whole J. And I want to emphasize here, for now, I don't assume anything. In fact, I will not assume anything on the rank of J of Q here. It's only enough to know about one thing in the quotient. So of course, the analogy is for rank 0 quotients for classical Chabauty. For classical Chabauty, if you have rank 0 quotient or even a quotient of small enough rank, you can apply the method and get results. Okay, so this would be the Same thing, but for quadratic Chabauty. And now we think, okay, it works for all this. Does it extend the method? The answer is yes and no. We have a condition, a little more condition, happens to work in some cases. And why? The reason is actually quite simple. There is L, such that if I call this pi by hypothesis here, I can find L such that the degree of the pullback, so is 0. So this belongs to log of J. Okay. By construction, that's what we can find. But I want here, what do I want? We want I got pi star L to be actually OC. And then if we have that, we can do the same thing as before, but going to A, we can extend the morphism from C to A to a lift from C to L. And we can basically do the same thing except over A and not over J, the Jacobian. So that the goal is to, again, modify this pullback to get something trivial. You just have to figure out, is it possible? And now, let's check out what this means. So take, for example, M, another element in the peak 0 of A. Okay, what happens to this? So first, I should notice if I do this. Okay, so I take L and pi star L. This belongs to peak 0 of C, which is J of Q, right? But if I take M inside peak 0 of A, L, it belongs to, sorry, first I should say, here belongs to peak 0 of J now, and then again I apply, here belongs to peak 0 of C. And as before, I want to use the right M so that this will compensate for the value I find here, which is an actual rational point in the Jacobian. Problem is the following. If I look at M to pi star M, it means I go from peak 0 of A to peak 0 of J, right? In other words, I have a morphism from A dual to J dual. I told you before that this is basically the same as J. All right, and now I didn't even use it yet, but I can tell you that this is isogenous. So it's almost isomorphism. An isomorphism, you can always find something like this. Even assuming, which is true, that this is actually the dual up to some isogeny of J to A, okay? This is a dual of actually, I'm sorry, exactly this, sorry. It's by definition, it's a dual of J to A here. It means I have a morphism from A to J. Am I sure I can get everything in J? Answer is no. So for example, assume, for simplification, that J is a product A times B with A and B, which do not see each other. In other words, no morphism from A to B. Okay, so if you think about simple factors, it means they do not have the same simple factors. They are really different. Well, here, simple factors of A have to go inside J. They will actually have to stay in A. They cannot, you cannot go to B by this process if you have this. So the image isogenous to A. Okay, so you don't see B. Now you might see the problem. There is no reason here for this point to be in A of Q. You might have a component in B of Q. There is a priori, I mean, you don't find any reason. It might be that in B of Q it has something, and then you cannot modify it, because whatever you do here, you just will apply elements in A of Q. So the right hypothesis is this. Assume that the group, so yeah, maybe I should say it this way. Say that I star pi star -1 of A of Q is different, is not contained in peak 0 of contained peak 0 of A. In other words, we want to ensure that there is a L here, so that the image here and L not peak 0, that this actually lands in A of Q. And if it lands in A of Q up to some torsion, which is fine, up to some multiplication, we can simplify it by a choice of M that will give us the compensation, right? But that is the right hypothesis. I'd maybe give a sort of an advertisement for next week. I'll talk about this specifically in the case of modular curves. Modular curves, especially non-split ones or extent of P plus, you're in a situation where classical Chabauty does not apply, but this can be found. You can find such quotients, but then this can be found easily by analytic methods. But then the problem is finding such a L. Okay. And the thing is, Higner points who behave so well for finding the ranks, it happens they behave also very well here. You can fix A where the ranks are the right ones. You call this the Higner quotients. You take all the maximal A like this. By definition, the supplementary B will be the ones where the Higner points vanish. They'll be all torsion. Now you can prove, this is not easy, but you can prove it, that when you build this thing and you apply on endomorphism, so basically by L, you do land inside Higner points, or some of the Higner points for B. So it means for the modular curves that are the ones we're interested in, this is actually not a problem. It's this, the space of these line models is actually as big as row A, and the space of row A. So you actually do get what you want. And you can apply the method. And so quadratic Chabauty does apply. Okay, maybe as a conclusion, moral conclusion. And also, Professor Fagate promised you the Q expansion principle. I'll just make one final drawing, final idea, and then we'll be finished. So what I just explained to you is that for infinite families of modular curves, we are able to, in principle, apply quadratic Chabauty. I mean, the method exists, right? But of course, we need to apply equations, etc. And I guess the current state is it's not applied until it applied until level 17 or something. So it's not very far because the equations are very large. So if you remember what Jan explained yesterday here, he gave some very good theorems based on actually based on Chabauty method here. And actually, they're also implicitly based on Q expansion of modular forms, which you'll see hear about this afternoon, I think. With this and this on modular curves, you're able to apply something, for example, Mazur's method, also applied, of course, in the work of Merel here and others. And what you can remember of it is that you don't need equations at this point. Once you can do everything with modular forms, at cusps, you don't need equations for the modular curve. Just need things of modular forms and not even very difficult ones. With equationless Chabauty. And then, for example, the extent of P of Q was found, etc. So if you have Q expansion plus Chabauty, you can work it out and you can determine a lot of points and a lot of modular curves. Now, as of now, our quadratic Chabauty, we have this method, which we know work in principle, could help us if we had equations to figure out the points, but we don't have any sort of interpretation for modular forms themselves. So the hope is something, but the dream would be to be able to do some equationless quadratic Chabauty to understand better how to figure out all this for modular curves using all their wonderful properties that we've hope convince you they exist, and they're very nice with my talks, Jan's talks, etc. So this concludes what I wanted to say about quadratic Chabauty with a bit of modular curves at the end. Thank you.
Any questions, comments?
Yep. Exactly. Okay. What means should fail? Yeah, not the QP rank maybe. Yeah. Yeah. No more, yeah. Yeah. Mm-hmm. Yes, you mean, so you're looking great, and maybe I'll draw it. So you have, yeah, let me do it here. So you start with this, right? L star here, and you want to apply a logarithm. So the log function I did before, right? Oh yeah, okay. So log L, right? Okay. Well, this is not. It doesn't have no structure, no, but it's not additive here. This is not a group. This is a GM torsor. And actually, this is one of the subtleties. I sort of hinted of this at the end. You can reinterpret many things for quadratic Chabauty, especially in a version called geometric quadratic Chabauty, almost exclusively in terms of torsors and by extensions. Basically, you have GM, you have J below, and you also have J hat, and because you want to do things dual, etc., you can have things that restrict to group laws over the bases, but there is a third direction, and there it's not exactly a group, something called a by extension. Actually, it appears also in what I said about the Poincaré bundle. When you restrict the log function, you do get log function on A and A dual, but there is a vertical direction which is we can build, but it's more mysterious. And actually, understanding it would be, I think, a very good step in applying the maybe a method in a better way. Yeah. Yeah. I don't think it has a natural group scheme structure here, because you cannot really add that's all the problem. Yeah, you also need it. Yeah.
Any more questions, comments?
Oh, the relationship between, I don't know. I can just tell it. Clearly, that's also why the Poincaré bundle is the main player in the story at the end, because of its universal properties, and you can just do things over A times A dual and hope it's enough. But yeah, I don't know exactly how to tie it up with other cases.
Any more questions, comments? Well, in case there are no more questions or comments, on behalf of all the participants and the organizers, let's thank Samuel Fourn for his wonderful set of lectures.